Okay, for this assignment, we're going to be looking at doing a Fourier series representation of x of t, and I'm going to define x of t as a periodic signal that looks like a sawtooth waveform. Okay, so this lasts for 2 seconds, 0 to 2, this is t, and this has a height of 2, and you just repeat this. So there's a sawtooth waveform. You know what periodic means. Okay, so to do the Fourier series representation, we talked about in class that we want the exponential form, and so that'd be looking at the sum from n equal minus infinity to infinity, Cn e to the minus j n omega naught t. Okay, so one of the things we know also is that you need to know the fundamental period of the waveform, and of course that's how often it repeats. Okay, so here's the start of a starting point on the waveform, and we notice that the next time that point occurs is 2 seconds later, and so the period on this is 2. Okay, because we know the period is 2, the fundamental frequency is 2 pi over cap t, so in this case the fundamental period would be omega naught equals pi. Okay, from there we need the Fourier series coefficients, and so the definition of that is integral 1 over t over any period x of t e to the minus j n omega naught t dt. And we can talk a little bit about how to apply this. And so what I need is an analytical function for x of t over one period. And so what you do, and you've practiced before, is you look over that first period, what is that mathematical function? And this is just an equation of a line as a function of t. It's really easy in this case, it's just t. Okay, it's got a slope of 1 and an intercept of 0. Okay, so what we're looking at here is for c of n to be 1 over 2, integral over any period, so let's do 0 to 2 of t e to the minus j n omega naught, but omega naught is pi, t dt. Okay, so that's the Fourier series coefficients exponential form. Okay, but the thing is, the complex exponential is used as a convenience. Okay, so sometimes we want to plot what the Fourier series would look like for x of t, and the catch is that the complex exponential is complex, and eventually it all works out where the real part is what's left when you do this summation. But it's a little easier if you just convert to a different form of the Fourier series for purposes of plotting. Okay, and actually some other types of analysis, it's a little easier to convert from the exponential form to the compact trig form. All right, so compact trig looks like this. X of t is going to be some c naught, that's the dc component, plus sum from n equal 1 to infinity of capital Cn cosine n omega naught t minus theta n. Okay, where the Cn's are 2 times the magnitude of the little cn's, and the theta n is just the angle of the cn's, and this is for n equal 1 to infinity. N equals 0 is a special case, so c0 is equal to little c0, the DC component. Okay, so once you have that, it's easier to do MATLAB I spelled that badly. MATLAB to plot your Fourier series representation. Of course, you can't go from 1 to infinity. You have to choose some stopping point in naught, and you let n naught get as large as you want and see what the plot looks like. Okay, so that's the setup for this homework problem. I'm going to give you some MATLAB code. It's actually a live script code, so you can see, you can click through there and you can see how you can calculate the Fourier series coefficients using the symbolic toolbox. You'll see how that goes when I do a little video talking about that. Okay, so that'll be in part 2 of this assignment. All right, so what I'm going to want you to do is I want you to repeat everything that we've done here for a different waveform. Okay, so the waveform that we're going to look at is